Okay, for this problem we want to take a disc, right, and cut a wedge from it, and then take what remains and roll it up into a cone. Okay, you've probably done something like that before. All right. In this case, what we want to do is find the cone of maximum possible volume. So step one, right, write down what it is you're trying to do. We want to maximize the volume. Right. Step two is to come up with a quantity. Right. While we're trying to maximize the volume of a right cone, right, is 1/3 pi r squared h. Right. Now, that's actually step three. Where's my notation? Right. R is the radius of the cone. So it's not this original radius over here, which is 5. It's the radius of the cone. The radius of the original circle becomes the slant height of the cone. If you don't believe this, take a circle and cut out a wedge like this and make a cone out of it. You'll see how it goes. All right. So this is not 5. This is the radius of the cone. We'll just call R, and this is the height of the cone. And the whole trick to this problem, or the trick to make this problem as easy as possible, is to realize that I've got a nice right triangle here, with R and H, the legs of the right triangle, and 5 is the hypotenuse. Right. Because now that I want to eliminate a variable, right, I can use that relationship, R squared plus H squared equals 25. Now, it's possible to set up this whole problem in terms of this angle theta, but the problem's quite a lot harder that way. It seems natural to do it that way. But this trick of using the Pythagorean theorem here, there's a Pythagorean right triangle sitting inside of this cone, all right, allows us to just ignore theta altogether. Right. I see I've got an r squared in my original function. I need to either eliminate the r's or eliminate the h's. Since I have an r squared, I can write r squared equals 25 minus h squared, and then substitute that right in. Right. And I get here in step 4, I get the volume as 1/3 pi r squared h, or pi over 3 times 25h minus h cubed. I'm multiplying the h through here to make the differentiation step easier. Right. What is the domain of this? Right. Well, h clearly has to be at least 0. And if I make r equals 0, I would have h equals 5, so we have h less than or equal to 5. So h is restricted to a closed interval. And having that closed interval tells us how we're going to do the calculus. All right. We need to find the absolute maximum volume, so the absolute maximum of this function over a closed interval. And that suggests we use the closed interval method. So for calculus, I'm going to take the derivative with respect to h. The pi over 3 here is along for the ride. 25 minus 3h squared. Set that equal to 0. That's going to be 0 if this is 0. I can just divide both sides by pi over 3. Right. So h squared times 3 is equal to 25. H squared equals 25/3. And h would be plus or minus the square root of 25/3. But I don't care about the minus because I can't have a negative volume. I'm restricted to 0 to 5. All right. Can't have a negative height. So our only critical number inside of our interval is the square root of 25/3, or square root 5 over 3. Okay. 5 over the square root of 3, excuse me. Right. Now to justify that I have a maximum there, I'm going to make a table of values. I don't have to list every possible h, just the endpoints and their critical numbers. And for each of those, I'm going to compute the volume. So my volume formula is here. If I plug in 0 for h, I get 0. If I plug in 5 for h, I get 0. So the only possible optimum, right, if you plug in 5 over square root 3 carefully into here and do some math, you'll see that you get 250 pi over 9 square root 3, which is about 50.38 cubic inches. Okay, that's the maximum volume I can make one of these cones from a 5-inch disc. Right. We're fortunate that it doesn't tell us to find the angle. We'd have to work backwards to figure out what that was. All right, good job.